Okay, so our speaker today is Ziyan from University of Copenhagen. Ziyan is currently a postdoc working with Ernst Johnson, but she has recently been awarded the Marie Curie Fellowship, so she will stay there and keep working with Ernst. Before that, Ziyan spent 3 years in France for her first postdoc after finishing her PhD in Peking University in 2021. And so today, Ziyan will talk us about from pebbles to planets. So take it away, Ziyan.
Okay, thank you very much. So as you can see, I'm talking about mainly about dust dynamics in planet formation, different planet formation processes. So to think about the process of planet formation, we actually can trace all the way back to the protostellar collapse phase, where you have this cold and dense molecular cloud, and this is basically collapsing and forming this protostar in the center, and then the circumplanetary protoplanet disk around it. And so this disk is believed to be the birthplace for planets, and it consists of dust and gas, which takes us to the second stage. So, and we know that the dust are actually the building blocks for planets, but actually the dust dynamics is heavily relied on the coupling between dust and gas, as I will also show you later. So the dust, to build up to planets, it has to grow all the way from micron-sized dust particles and all the way to the planets, right? So the first, they have to grow mainly by coagulation, meaning that very small dust grains basically collide and stick to each other. And then they can grow to this millimeter or centimeter sized pebbles. And then these pebbles have to grow to kilometer-sized planetesimals, which is the second stage. And then when these planetesimals are massive enough, they will further go through core growth, and then probably also gas accretion to finally form the planet. So in this talk, I will try to cover all of these different stages if I can, time permitted. So hopefully I will. So the idea is that every time when I finish one stage, I will ask you to ask me any questions, and then I can go on to the next stage. That's basically the plan, if I can finish. Okay, so now I will just start with the second stage, which is planetesimal formation from pebble-sized dust particles. So one of the most widely believed and most successful way to form planetesimals is by streaming instability. So here is one way to understand how streaming instability works. So basically, you have this disk consists of dust and gas, right? And the dust in the gas in the disk is rotating at subcapillary velocity, but the dust is rotating at capillary velocity. So the dust will feel this headwind of the gas in the disk. So because of the headwind, they will lose angular momentum, and then they will drift inwards radially in the disk. But this is basically because when we consider the aerodynamic drag from the gas to the dust, right? But if you also consider dust feedback, which is the back reaction from the dust to the gas, then this whole effect will be weakened. And so if you have stronger dust feedback to the gas considered in the scenario, then the radial drift of the dust will be slower. So now if you consider in the disk, you have somewhere denser distribution of the dust compared to other, then this denser region will in general have stronger dust feedback. So this region will tend to drift slower than average, right? And then the other parts where there are less feedback will drift faster, so they will pile up to this dense region and make this region denser. And then this denser region will have even stronger feedback and drift slower, and so this can trigger this feedback, right? So this is basically what we call a traffic jam of dust particles, which can pile up at these overdense regions in the disk. So now we have this, and then this is a simulation movie showing you how streaming instability looks like. So basically, it's lagging here, but basically we can see that as time goes, you have this clumpy structures of the dust, right? And this is where you can further form planetesimals. So there are three very important factors for streaming instabilities to operate. First is the gas pressure gradient, because only with that you can have the radial drift of the dust. And second, you need dust feedback to gas so that you can have slower regions when there's denser in dust. And finally, you have to reach a certain level of local dust-to-gas ratio. Usually, people believe it should be higher than 1, but I will discuss later. This is also a lot of details here. Because the higher dust-to-gas ratio you have, the stronger dust feedback to the gas is, and then the stream instability is more strong in this case. Okay. So now we know that stream instability requires a local dust-gas ratio, but how can we actually have a higher dust-gas ratio in the disk? So one way is when we consider there's the vertical settling of the dust grains. And then with vertical settling, the dust is concentrated to the midplane. So the midplane is naturally higher in local dust-to-gas ratio compared to the averaged one, right? And then, so if assuming you have this certain level of dust settling in the layer, you can basically translate the local dust-to-gas ratio condition to the condition of the global metallicity for triggering stream instability. So this is what they see. Basically, they have this simulation of vertically stratified dust layer, and then they can see dust clumping in the midplane. And then when these clumps are dense enough to reach the Roche density, then the self-gravity can take over. So here is another simulation showing you when self-gravity is included in the simulation, then these clumps can basically self-gravitatively collapse and to form the planetesimals. So that's how planetesimals are formed. And I was already talking about this criterion for stream instability to work. So basically, I told you that you need high enough dust-gas ratio, but actually it's more than that. So this is previous work by Ziyan and Andrew. So basically, they show that they run a lot of different simulations with different metallicities in the disk and different sizes of dust. So smaller dust will have smaller particle stopping time or Stokes number, and larger particles will have larger stopping time. So basically, they run all the simulations and they can basically map which conditions have dust clumping, which ones does not. And then they have this green curve, which is their clumping criterion for stream instability. So basically, above this curve is the region where stream instability can lead to dust clumping and further lead to planetesimal formation. And the lower parts are when it doesn't. So you can see that this criterion is heavily dependent on the Stokes number or the particle size. So, and it's most effective when the stopping time or Stokes number is around 0.1, where the lowest metallicity required for stream instability to clump the particles is around 0.005. So this one is the case when we don't include the external turbulence. But as we know, in reality, the disk is turbulent, right? And we also need to consider turbulence, but actually, depending on how exactly we treat the turbulence in a disk, things can be very different. So for example, in this simulation, if they just manually impose turbulence in the simulation, what I see is basically planetesimal formation can be suppressed, right? So without turbulence, you can see this clumpy, like dust clumps in the red circles. And then without turbulence, with turbulence included, basically they cannot see the clumping anymore. This is basically because turbulence is diffusing the particles everywhere, so it's just harder for them to clump. But then if you consider another scenario where they imposed MRI turbulence under ideal MHD, which is one of the dominant natural sources of the turbulence in a disk, right? So with MRI turbulence, it can actually generate this kind of so-called zonal flow. So they can generate this sort of local pressure variations or even pressure maxima. And so this structure, like local pressure maxima, can actually help concentrate dust particles therein. So this effect can actually enhance planetesimal formation within this zonal flow induced structures. So as you can see, we depending on how exactly we treat turbulence, we have to be very careful about this. And so now that we're thinking about turbulence, so recently there's also work about how the clumping criterion will be changed if we consider turbulence. So here is basically what the result is. Again, they run a lot of their simulations with different stopping time and different local dust-gas ratio, right? So they basically get this new curve, which is their new clumping criterion. So comparing to this one with the blue one, which is the previous one without turbulence, they basically say that the clumping criterion is higher when the turbulence is included. And they also tentatively see that this criterion is likely independent of the alpha in the system, but it's not very strong conclusion there yet. And so this, I want to mention that this clumping criterion is for the local dust-gas ratio. So basically it's rho d over rho g. But what we actually see from the observations is actually metallicity, which is vertically integrated, right? So it's the surface density between dust and gas. So they also try to compute that. And so this is a surface density dust-gas ratio as a function of Stokes number. And they all actually tried different alpha, different strength of turbulence, and they see that actually this criterion is increasing with higher alpha. So basically what is happening here is that at the mid-plane, you always require a similar dust-gas ratio to have clump. But then if you have stronger alpha, then your disk is more popped up. So in order to reach the same criterion at the mid-plane, in general, you require more dust-gas ratio vertically. So that's basically how the alpha is changing the criterion in terms of the solid abundance. And so you can see in these three different alpha, you can basically see the metallicity is required for clumping is generally higher than 2%, and it's even 4% for this case, right? So these are all in general higher than the solar metallicity. So which means we still need something to further enhance the local metallicity, even considering the dust settling, because this metallicity doesn't care about the settling, like it's already vertically integrated. So what can we have to further increase this local metallicity? Actually, dust ring can do this. So as we already see, there's a lot of ring-like structures observed from the ALMA dust continuum. These can be very ideal sites for planetesimal formation because it's believed that dust rings are basically a gas pressure bomb that can trap the dust. So with locally dust concentrated in this very narrow region, and locally the metallicity in the ring can actually be enhanced just because of this radial concentration. But there are still problems. First is that the conventional hydro streaming instability is not expected to happen exactly at the center of the bomb, because as I told you before, streaming instability requires a pressure gradient to form, but exactly at the center of the bomb, there's no pressure gradient. So things can be complicated there. And again, rings are supposed to be turbulent environments, so we also need to take that into account. So that's why we want to basically answer those two questions. First is, do dust particles still clump to form planetesimals in the dust traps? And second is how the dust feedback can affect the dynamic of the dust in turbulent dust rings. So to answer these questions, we have this 3D non-ideal MHD simulation with Athena. So basically what we're doing is that we manually driven this pressure bump in this local Chiron box. So you can see you have this gas, projected gas bump structure like this. And then we also throw in dust particles in the simulation. And so because we have the background pressure bump, so the dust is concentrated in these ring-like structures. And so we have non-ideal MHD with amorpolar diffusion, which give us a fairly realistic MR turbulence. So alpha in our simulation is around 10 to -3. So it's very realistic, I would say. And for this case, we mainly focus on Stokes number 0.1, which is supposed to be the most efficient particles. But I will also talk about other Stokes. So here's an overview of what happens in the simulation. First, we see that there are dust clumpings. Like you can see here in the simulation, you can see these very bright dots, which are dust clumpings, right? But this clumping is only seen in the case with dust feedback included. If we don't consider dust feedback, then we don't see this kind of clumping. So no matter what is driven this clumping, it requires dust feedback. And if we measure the maximum dust density in the simulation and plot it as a function of time, we can see that so these lower layers are lower curves are the case without feedback. But then as long as we have feedback included, you can see the maximum dust density is much, much higher compared to the one without. And so this maximum density is actually reaching or exceeding the Roche density, which means that in the simulation, these clumps are already sufficient for planetesimal formation. And so now we see the clumping properties. We also wonder how the dust feedback can affect the dust ring properties. So it's actually very obvious to see that actually when dust feedback is included, the rings are much narrower compared to the case without. And if we look at the edge on view, we also see that the dust feedback is making the dust layer also thinner. So basically, dust is more settled to the midplane when dust feedback is included. And both of the is basically, we think it's because dust feedback can change the MRI turbulence properties, which I will also talk about later. Okay, so now that previous one, we only have one dust species with Stokes of 0.1, but now we wonder, what if we consider different sizes of dust for both theoretical and observational reasons? We are interested in that. So that's why we extend a previous simulation with multiple dust species. So now we have 7 different dust species. So the largest Stokes number is again 0.1, but then this time we can go all the way down to 0.001 of Stokes number. And as you can already see, basically as the Stokes number goes higher, you have narrower ring and also much thinner vertical layer. And so if we actually, because we have multiple dust species, so we can actually calculate or measure the ring width, and they can plot it as a function of Stokes number. So here's how it looks like. This is a little bit busy plot, but basically if you look at the gray data points first, those are the case without dust feedback. So at least for the larger grains, those data are fairly well matching the theoretical expectation of the alpha over Stokes. And for those smaller, it's basically because the ring width, the ring width here are basically dust ring width is same as the gas bond width and cannot exceed more. So that's why this part shouldn't really follow this slope. Okay, so this is for the case without feedback. And then all of these colorful data points are the cases with feedback. So again, you can see basically the dust ring width is much narrower as long as feedback is included. And also depending on, so each color corresponds to a different solid abundance in the simulation. So in general, we figure out that the higher solid abundance we have in the simulation, this reduction of dust ring width is stronger. So basically, when we consider, so it tells us that when we think about dust ring width, of course we need to consider the alpha, the Stokes, but also we need to consider the dust gas ratio. The higher dust gas ratio, the actually narrower the ring is compared to this one. And also again, of course, this reduction is more clearly seen for the large Stokes numbers, and for small Stokes, because they're basically coupled to the gas, so that they don't really feel so much about this feedback thing. So this is for the dust ring width. We can do the same thing for the scale height, and basically we see very similar patterns. So dust scale height is also reduced when feedback is included, and this is also stronger when you consider more higher dust gas ratio. Okay, and then so now that we know that both the ring width and the height are reduced, we want to see what exactly is happening. So we check the density radial density, the dust density profile on the radial direction on the top and vertical direction on the bottom. So basically, if we focus on the top one first, then different colors is different Stokes number. So if we just focus on the largest Stokes number, which is the blue one, you can see, so the solid one is the one with feedback. The dashed blue line is one without feedback. So without feedback, you can see it's fairly nice Gaussian profile. But when feedback is included, then the radial profile is not Gaussian anymore. It's basically forming this cuspy structure towards the center of the ring. And this is also seen if you look at the vertical profile, right? So it's also fairly a nice Gaussian when there is no feedback, but when you consider feedback, they're settled, the dust is settled more to the midplane, but not maintaining this Gaussian. So it's basically like forming this super dense cuspy region at the midplane. That's why the overall dust layer is more is thinner. And then, so if we directly look at the ring from the edge on side, you can see the dust is basically concentrated at the midline and at the ring center. And another thing we noticed is that, okay, so we can plot also the RMS gas radial velocity as a function of like spatial resolution of it. And we noticed that this location where the dust is concentrated, exactly at the same place, the RMS gas velocity is much lower compared to the ambience. So this is basically saying that the alpha, the turbulence diffusion in the center of the clumpy ring is much reduced. So this can be very interesting because imagine you are observing this ring, which is very narrow, right? And then you can basically estimate this alpha over Stokes in this narrow ring. But then with the alpha you're measuring, it's actually the alpha here. That's why maybe you have very low alpha from the ring, but actually it doesn't necessarily reflect the alpha in the disk or even outside of the dust ring range. So I think this is something that people should be a little bit careful about when thinking about this very simplified alpha over Stokes estimation. Okay, so that was about the ring properties. And now let's look again about if there's dust clumping in the rings. So basically, what we're doing is that on the left-hand side, you can see this is the maximum dust density as a function of time. But we plot each color is a different simulation with different metallicity. And then, so basically, we can see that when the overall metallicity is higher than 0.005, we can see this dust clumping here. But then if we run another set of simulation where we remove the biggest particles, so we only have those five fairly smaller types of particles. So now the biggest Stokes number is 0.02 instead of 0.1. And when we do this, we can see that we again try different metallicities. And this time we see metallicity required for clumping is 2%, which is much higher than this one. So basically, this is telling us that the clumping is basically determined by the abundance of the largest particles in the system. And if we have a largest maximum Stokes number in the system, the clumping will be easier. If we have smaller maximum Stokes number, then clumping will be harder. So again, because we tried all of these different simulations, now we can plot the simulation results back to this map of clumping criterion. So basically what you're seeing on the left is, again, this curve by J. Lim with turbulence, this curve without turbulence by Li and Yudin, and then our simulation results in red. So basically, you can see that when we consider a turbulent ring, the clumping criterion is more or less going back to the case without turbulence. So it means that probably even when you consider turbulence in a turbulent disk, when you have a ring, because the ring is concentrating the dust very efficiently, so the streaming stability actually do not require such high local dust gas ratio anymore. And again, because we want to also compare with observations, so here is a map for the vertically integrated metallicity in the ring, right? So you can see basically our result is generally consistent with previous two results. So basically our result at Stokes of 0.1 is generally consistent with previous results with alpha of 10 to the minus 4. But then our result at Stokes of 0.02 is more or less consistent with the Stokes of higher Stokes with the alpha of 10 to minus 3. But we have in the same simulation, right? So basically, I think this is telling us that because different sizes of particles are distributing in different regions, so the large particles are distributed in the ring center where they can feel lower alpha. And the smaller particles are distributed away from the ring center where the alpha are higher. So I think that is why in the same simulation, we're matching with different previous simulation with different alphas. Okay, and now that we have the clumping criterion for the rings, we now wonder which rings from the ALMA are clumping. So we are currently trying to basically collect different Z and Stokes number from different observational results and try to put in the map. But here is just to try and show you one example from previous work. So this is basically they try to do this one case. So there are basically two rings in this case. So they can measure the dust surface density from the ALMA, and then they can also measure and model the gas surface density. And so they can get the metallicity in the ring. And then they can also, because of the gas surface density modeling, they can also get a Stokes number. So basically they can put the two rings in this clumping criterion map. And what they found is that when comparing with the map without turbulence, then the outer ring can be in the clumping regime. But if we consider this criterion with turbulence, then both of the rings are sort of outside of the clumping criterion, meaning that they're not very likely that these rings are like dense enough to trigger a streaming instability. So, okay, so this is just for one case, and for now I'm just trying to get more, but the question is it really the case that the rings are rarely clumping when the turbulence is considered? So we can see from here that the problem for these rings, of course, is because of dust-gas ratio, but I think more importantly, it's because these rings generally have much smaller Stokes number than the region that the streaming instability is supposed to be efficient. So I think that is one of the major problems. So if we go back to this plot where you see in the rings, the turbulence level is much lower, right? If the turbulence level is much lower, it means maybe the collision speed is much lower in the rings. So maybe there can be dust growth there. So if we consider dust growth, maybe it can solve the problem where the rings are having too small Stokes number to go into the streaming speed. So I think I will briefly stop here if you have any questions in this part. If not, I will go into the dust growth part.
One question on the previous slides. I'm not following very well. So what is the main difference between this work and the Booth et al. 2019? Is the gas mass is different?
I think they use different modeling to get different gas surface density. So Booth, so they have their own modeling, and then this one is according to the modeling with this previous Booth et al. But I think the gas surface density also has a lot of error here, so it's a lot of uncertainty here. So
yes, so your simulations, they go up to Stokes number of 0.1.
Yes.
Now looking at this figure, is it because it's motivated by observations? Otherwise, I would have thought that you would be interested to go higher, right? To go to Stokes number closer to 1, right? Because those that drift the most.
Yeah, but according to the previous clumping criterion, actually this one, the most efficient one is actually around Stokes 0.1 for streaming.
So they went beyond 0.1 and they show that it's not that efficient.
Yes. So yeah, I can go all the way back. Show the.
Sorry, I missed that.
Yeah, it's this one.
Okay.
Oh, this one. So basically so that's why most of the streaming instability simulations are motivated by this kind of curve where they choose Stokes 0.1 as the easiest case.
Okay.
But actually, if we're really motivated for observations, we should go to much smaller Stokes number. I think that's what the current problem.
That criteria still hold with non-uniform turbulence, right? Models.
Yes. So all of these are with turbulence.
I mean, for the green Stokes number, you can go to 1. Maybe that still can work with high turbulence.
I think for our case, the red one, no, because we don't cover higher Stokes number, so we don't know. But at least for this one, I think they should have even higher Stokes number. So they give actually this analytical recipe for calculating the criterion. Okay, if there's no other question, I will quickly go to the part where I want to talk about dust growth, because we see that dust growth can be one.
Quickly, could I ask one thing? Can you hear me?
Yes.
Yeah, so first of all, excellent work. Thanks so far. I was just curious on the comparison to observations. How certain are those Stokes numbers from the observations? I noticed that that paper has some somewhat surprisingly low error bars. So I don't know if you could comment on that.
Yeah, I would suppose as you can see, just because of, as you can see, the two data points here are the same ring and two different models. So actually, I think the distance between the two 100 AU ring should also represent somehow their part of their uncertainties, right? So basically, for the same ring, just because of different modeling, they can get such a different metallicity and Stokes number. So this tells you how model dependent all of the values are. And the error bar is just for each one modeling, right? So, but I don't know if observers have better idea in this, but I think it's really highly uncertain in each of the rings.
Okay, thanks.
Okay. So let's go back and talk about dust growth. Okay, including this. Okay, so the reason why we want to study dust growth partly is because, as you see before, the Stokes number are too small in the rings, right? But also motivated by recent works. So here's one work. They actually have this streaming instability simulation with a lot of particles, and then they measure the collision speed in this streaming instability simulation, so they can get the coagulation timescale for streaming instability. And what they see is that actually streaming instability can lead to a shorter coagulation timescale, meaning that now if you consider that, then of course, at the beginning, if you have very small Stokes number, you are not in this clumping region, but it's okay because you have streaming instability, which can make the small grains grow larger. And as you grow larger, you can basically, like when considered coagulation, you can grow into this regime where you can clump. So because of this, the range of the clumping regime is more extended towards the smaller Stokes number, which is really nice. So this is how streaming instability can help coagulation. But on the other hand, there's also another simulation showing that coagulation can also promote streaming instability. So this is a simulation where basically, again, have streaming instability and does coagulation, and they assume each row is different fragmentation velocity. So basically, if you have high enough fragmentation velocity, you will have very large Stokes number at the midplane. And because of higher Stokes number at the midplane, that's why you can have clumpings, right? So basically, if your fragmentation velocity is really high, even starting with a very small dust particles, you can grow into the large Stokes number, and then you can basically clump as large Stokes number particles. So when combining those two things together, right? So streaming instability can help dust growth. Dust growth can help streaming instability. So maybe if we combine those two together, we can have this sort of runaway streaming instability clumping, which is super nice, right? And just when I was thinking about this idea, and this paper came out, like the second day. So this is a semi-analytical work combining both streaming instability and grain growth. And basically their point is that there can be a positive feedback loop between those two processes. So if we consider both streaming instability and dust growth, and then it can basically boost each other. And so now if you look at the clumping criterion, basically you can have much lower dust gas ratio and much lower Stokes number required. So basically these particles can basically grow and clump, and eventually grow into this clumping regime. So now this is really nice, right? So it's very encouraging because we see that even for small particles, it can eventually participate in this clumping. So this is very interesting, but this is again still semi-analytical work, and we want to do simulations about it, right? And if we go back to this paper before, this is a simulation, but they require 100 dust bins, and this is a 2D simulation. And also their problem is that they don't have self-consistently calculated collision speed from the hydrodynamics. So basically, they are not feeling the different collision velocity because streaming instability happens. So because of that, their growth and the streaming instability are not talking to each other. So their simulation cannot have this sort of feedback loop. So in order to have this, we have to, in the simulation, have coagulation, streaming instability, but then make those things talk together. And so basically that's the idea. And that can be more computationally expensive. And especially if we consider simulation with coagulation, basically the accuracy heavily depends on how many dust bins you have. So usually for the hydro simulation, 3D simulation usually requires like hundreds of bins, but the computational time can go n squared or even n cubed. So we really cannot afford 3D plus 100 bins, right? So this is what's showing you the problem of having less bins. So when we have less bins, and then basically towards the larger size of particles, the density distribution will become diffusive compared to the analytical solution. So this is basically why we need more bins so that this part can go back to the analytical ones. And so recently, there was a work by Lombard and Lab. They developed a higher order solver for the coagulation equation. So basically the idea is that you have these dust bins, right? And then they can basically interpolate with higher order of this any distribution in the bin. So because of this, they can achieve higher accuracy with lower number of dust bins. So now with this included, they can basically require only 20 bins for basically accurately solve for the coagulation equation, which is a huge improvement compared to previous 100 bins required. And so now we are trying to implement this higher order algorithm into Athena, the simulation. So basically, I will skip the details, but basically what we're trying to do now is to implement into dust fluid module in Athena. And we're now just trying to get at each time step, we get the dust size distribution. We do the coagulation equation, we get new dust distribution, and then we update as a source term in the dust. And then we can update at each time step or at each dt that we want in the simulation. So there's still a lot of numerical tests in progress, but I just want to share with you the current state. Basically, you can see, so here we have zeros order, so the conventional algorithm, 20 bins, which is diffusive, you can see here. And compared to this one, we have 100 bins, so you can see here. This is supposed to be closer to the accurate solution. And this one at higher end, there is very diffusive sort of tail. So this is why we cannot use 20 bins. We have to use 100 bins for the conventional one. But now, if we consider this higher order interpolation, you can see basically this part is getting much closer to the profile. So if I shift, you can see this one is more diffusive. This one's less diffusive. More diffusive like this, less diffusive. So this is all because we implement this higher order algorithm. So now there is still a lot of numerical tests to do, but hopefully in the near future, we can accurately solve this coagulation with hydrodynamics, with stream instability, and maybe with 3D with a lot of different physics ingredients in the near future. Okay, before I continue, is there any problem, questions in this part? Okay, yes. Okay, let me just quickly go to the planet formation part. So in the core accretion scenario, the planet formation, the planetary core can grow rapidly by pebble accretion, that is creating pebble-sized dust particles. And at the same time, the core not only accreting pebbles, but also accreting a gas envelope surrounding it. And then this envelope is still embedded in the disk, right? But then the disk is not, the envelope is not isolated, it's embedded. It means that it can have a lot of material exchange between the envelope and the disk. So this is a previous simulation showing a gas streamline where you can basically, the gas from the disk can penetrate very deep in the envelope and spirals and then go out. So there's a lot of exchange between the envelope and the surrounding disk. And if we consider pebble accretion, then the accretion heating can actually play a very important role in setting the thermal structure of the gas envelope. Because if you have a pebble like accreting to the vicinity of the core, then the accretion heating can basically heat up the internal region of the gas envelope. So the inner part of the envelope is hotter, the outer part is colder. And because of this, you can have different thermal structure. So this previous simulation shows there can be a 3-layer structure where in the inner part you can have a convective layer in the envelope. So this convective layer is the focus of my talk today. And also there's basically previous work showing that this the temperature structure can go beyond boundary radius. It can go basically isothermal, and then so within, well, largely within boundary radius, you can think of it's like convective zone, and then outside of boundary radius, it's not convective, it's radiative zone. This is like the, well, it's zeroth order approximation that people are using. Okay, so because we have convective envelope, then the dust dynamics can be changed. So there is a simulation showing you how the Pebble accretion can be affected by the convective envelope. So you can see this is the trajectories for different sizes of particles. If you have large enough pebbles, then the pebbles doesn't care. They basically still get accreted onto the core. But then if you have small particles like the green one or the blue one, because there is the convective motion of the gas, so the pebbles can be moving around, and so the trajectories are more messy. So if they really measure the Pebble accretion rate with convection and without convection, actually they don't see so much difference. And why is that? If we further measure the accretion efficiency, then it shows the difference. So without convection, basically you can see that it's the accretion efficiency remains at a fairly high level, especially for this purple line. But then when convection is included, then the accretion efficiency is much dropped, especially for the small particles. So basically what's happening in the convective envelope is that convection is significantly mixing the materials, so it can kick out pebbles, but it can also bring in pebbles. That's why the overall Pebble accretion rate is not changed. But if you think about the accretion efficiency, then because it also brings in much more particles, right? So it's something divided by a large number of influx. That's why if you look at accretion efficiency, then it's highly reduced. Skip this one. And so I was also talking about the recycling flow in the disk, between the disk and the envelope. So if you still remember this, then if we combine the recycling flow and convection, what we can see is that with and without convection, the materials from the envelope can evolve differently. So this is a previous simulation by Zhao Huanzhu. You can see initially, if you put some gas tracers around the planetary core, if you have convective envelope, then basically the convection can mix all of the materials up outside of the envelope, and then the materials can all be carried out by the capillary shear or by the recycling flow. But if you have a radiative case where you have no convection, then only the outer part can be carried out, be recycled by the disk. But the inner part is protected because you don't have convection to mix this part outwards. So this can potentially means that the convection can help the recycling flow to penetrate even deeper to the envelope, so that in their case, the whole envelope can be recycled back to the disk. And this can be very interesting, particularly also because the convection can also impact the volatile recycling in the envelope. So, okay, so imagine you have this thermal structure of the envelope, and then you have convective envelope here, where you typically have this range of temperature between 200K and 1000K. And then if you have some species with sublimation line that is located within the envelope, then what will happen is first, the pebble will carry the volatiles inside here. And as the pebbles go through the sublimation line, the volatiles will be sublimated and released in the envelope. And because the envelope is convective, so the materials, the volatiles can be mixed and transported upwards by the convective flow. And then when they reach this recycling layer, they can basically lost in the recycling flows. And because of this, you can have volatile depletion. So only the dry pebbles can be accreted to the core, and the volatiles can basically be lost back to the disk. So this may apply to different species as long as the sublimation temperature is within the convective envelope. So this can be moderately volatile elements. It can be some organics, and even water in some cases. The water ice line can reside in the convective envelope if you're at outer disk environment. So why we are interested in this is because so in our group star plan, half of our group members are cosmochemists. So they are interested in how the volatile depletion in the Earth is happened. So basically, they measure the volatile abundance in the Earth, and they see this depletion pattern, and they want to understand. So, and we are trying to see if the volatile recycling and convection scenario that I explained before can potentially explain the Earth's volatile depletion. But at the same time, we want only the volatiles to be depleted. We want the pebbles to still be. So we really want to hit the sweet point here. And so that's why, again, I'm doing the simulation, but I think I will skip the details. I will just show you how the simulation looks like. So this is the tracer particles in the simulation, tracing the volatile movement. So basically, because of convection, you can see they are mixed outside. And then you can also see this is the radial velocity here, which is basically a subsonic convection. And I will skip, but basically the point here is that compared to previous studies, these are all consistent. So meaning that, well, our numerical setup is basically making sense. It's a robust numerical setup to have this sort of convective envelope. And then now it's time to look at the Pebble accretion. So actually I want to explain. So basically what we're doing is that we have small, intermediate, large, different sizes of pebbles in the simulation, initially distributed like this. The colors are basically their initial locations. And we just want to see how the pebbles where the pebbles will end up. So they can either drift toward the center, get accreted, or they can drift out, get removed by the recycling flow. And so you can see that for small pebbles, basically, if you look at the fractions here, basically most of like 90% of the pebbles are getting recycled. But then for the large pebbles, you can directly see from a movie, all of the pebbles are getting accreted, well, it's getting accreted to the center. So basically, it really depends on the size of the pebbles. And if we plot the accretion efficiency for those three different pebbles as a function of Stokes number, then basically you can see that the accretion efficiency is almost 100 for the large pebbles, and still like 80% for intermediate pebbles, and it's only dropped when the pebbles are small. And this is also consistent with previous work. So basically, this is telling us that pebble accretion is still efficient, and the convection is only affecting the smallest pebbles. So, but those pebbles are not the main contributor to pebble accretion anyway. So now that we have the pebbles, now it's time to look at the volatile transport. So what we're trying to do here is, again, I have this tracer particles tracing the volatiles at the beginning, and we see where the volatiles end up. And then basically, as the simulation goes, you can see they just directly get mixed out, and then many of them get lost from the outer boundary, which is lost in the recycling flow. And now we reach 1 year, and there's only 30% remaining. So basically, tells us that the typical volatile loss timescale is only 1 year, which is much shorter than the accretion timescale, like the pebble accretion timescale. Okay, so the point is that in the convective envelope, the volatiles can be lost in a really, really short timescale. So then we can make this simple assumption that assuming that the pebble accretion will stop delivering volatiles to the planet as long as we reach the previous state where the envelope is convective and hotter than the element's sublimation temperature, right? Then depending on different elements with different sublimation temperature, you will have a different point where the pebbles will stop delivering this certain element. So that's why the total abundance of the element will be different. And then, so basically this is our collaborator. We're basically assuming this and getting this 1D model, applying this into different elements, and then they can get this very nice model, assuming pebble accretion, this gray one. And then they also combine this pebble accretion model plus the planetesimal formation model, which is the dashed yellow one. and then plus a giant impactor model, which is the dotted one. And applying all of the three different accretion models, they can get a very nice match with the Earth data point. So this may tell us that the Earth was formed by the hybrid accretion pathway of all of these accretion processes. And I think I will just skip this one. This is basically the part where I also want to consider recondensation, but then recondensation onto small part, onto different sizes of pebbles also matters. So if we really, the volatiles are recondensed onto big pebbles, then they will basically pile up at the sublimation line and will never get diffused out. So this is something that we're trying to figure out if it's important or not. And I will skip this. And I just want to mention that before we're also always thinking from the perspective of planet, so that volatiles can be depleted in the planet. But then those volatiles are recycled back to the disk, right? So it can also be enriching the volatile abundance in the disk. But then does the disk really care about this enrichment? It really depends on this, if the pebble filtering is efficient. So basically, the pebble accretion, the fraction of the pebble accretion rate versus the total pebble flux is giving you how much pebble are processed by the planet. And then this fraction can also tell you how much the volatile can be enriched in the disk. So if you have this very giant, very massive planets, like a few Earth masses, it can actually generate this enrichment about 10% or even higher back to the disk. So I'm also wondering if this can also matter from the observational perspectives. I think I really am running out of time, so I will just probably skip this part and directly go to the conclusion. Okay. So basically in my talk, I didn't cover the stage 1, but the stage 2, I was talking about dust clumping in a realistically MRI turbulent dust rings can be sufficient for planetesimal formation. And also I talked how dust and gas interaction can change the ring properties. And also I talked maybe the dust growth can even enhance this whole process and can maybe solve the problem where the Stokes number in the rings are too small for the streaming slip to clump. And then I also talked about planet formation by pebble accretion, where we assume this core is in the convective envelope. And then we see that the pebble accretion still remains efficient in the convective envelope, but then the volatiles can be lost very rapidly. And this volatile loss combined with other accretion models may tell us how the Earth was formed. So I will stop here and take questions. And if you would like to talk about protostellar collapse, I'm also happy to have private discussions. Thank you very much.
Any questions? Kathy, do you want to speak up?
Sure. Can you hear me okay?
Yeah.
All right. Thanks for this really beautiful work. I had a quick question on the last part about the pebble accretion and retention in the atmospheres. Are you using fixed Stokes number pebbles or fixed sizes?
Yeah, so these are with fixed sizes. So in all of the movies, when I talk about Stokes number, I mean Stokes number in the disk. And then when the numbers, because that's when people think about pebble accretion. But then when the pebbles go into the envelope, the Stokes number will be much lower because
right. Okay, so that's what I was wondering about, whether or not there would be a shift. But so when you were using the reference for the 3 different sizes, that's based on the background disk.
Yes, exactly. Okay. So these are also, yeah, I didn't mention. So on the corner here, I say pebble Stokes number in the disk. This is what I mean by the Stokes number marked here.
Okay, and for example, what's the density contrast? So what's the effective Stokes number for the large pebbles by the time they get into the atmosphere, the envelope here?
So if you just look at the density.
There you go. So factor of 100, okay.
Yes.
Okay, great, thanks. It's really nice work.
Any other questions?
I guess if I remember correctly in the Zhu paper, the fiducial model was not convective and sort of had convection. You needed some big dumpster, like a lot more opacity.
I think it's what's the opposite. The fiducial
the
one
opposite?
is convective, and when you have big dust or when you have a hotter disk, you are not convective anymore.
Okay, yeah, I guess I'm mostly curious in your simulations. What is driving the convection, I guess?
Yeah,
Is
so,
it
yeah.
large luminosity due to the accretion?
Yes, so actually, because I skipped this this slide. So yeah, so it's basically following their recipe where there's heating and cooling. The heating is basically caused by the pebble accretion luminosity, and I assume the total luminosity and I distribute as a function of radius in the envelope. This part is the same as John 1's simulation. And then the difference is that we don't have radiative transfer. So we have beta cooling outside of boundary radius, and we don't have any cooling from within the envelope, assuming that it's optimally thick.
So how do you choose beta, I guess?
Beta is chosen to be around 1 over omega, so it's dynamical time scale.
Other questions?
Yes, and I'm curious, thank you very much for all these nice results. So are your pebbles on Earth mostly local within the small line, or they are outside the small line? And what is the pebble mass flux that you need for Earth?
Are you asking about my simulation or like in general? I think in general, I don't remember exactly the values, but the pebble equation is much more efficient at for giant planets compared to the Earth. And for the Earth, so your question was the pebble flux or
How many pebbles do you need?
how many pebbles?
I mean, in terms of mass.
So I think if maybe this can help. So I don't have values in my mind, but hopefully these figures help. So assuming that your core mass is at 1 Earth, and then the pebble accretion rate is around 2% of the pebble flux. And assuming, so you can assume that for a accretion timescale of 1 million year, and then you can assume the pebble flux to be 1 to the 6th Earth mass per year, and then divided by, well, multiplied by 100. So I guess it's going to be 1 to the 8th Earth mass per year. That's quickly.
1 to the 8th Earth masses.
That
seems a lot.
correct? Oh, sorry, let me think. 6. Oh, sorry, 1 to the -4. I wanted opposite. So if your accretion, if your accretion rate is 10 to the -6 Earth mass per year, then according to this one, then the mass flux will be 10 to the -4 Earth mass.
For a million years is under Earth mass.
Sorry?
For a million years is under Earth mass.
For
to
me,
extent for a million years.
yes.
Yeah.
Andrew, do you want to ask a question?
Yeah. So again, really nice work. So I guess I'm wondering, you're showing that you need these relatively large pebbles to be able to overcome convection and accrete, but then there's also the goal of keeping the volatiles out.
Yes.
I guess I'm wondering how that's sort of consistent with the larger pebbles. Would they actually lose their volatiles, or, and it takes some time for them to evaporate. So I guess I'm wondering if the larger pebbles would actually carry some of the volatiles with them.
Yeah, so I think, I agree that there's a lot of microphysics that has to be considered here. For what we're doing now, we assume as long as the pebbles reach the sublimation temperature, it's just like immediately lost the volatiles. But then, of course, if for example, as I showed for this case, if volatiles can recondense onto pebbles, and if they recondense back to the large pebbles, then these large pebbles will just drift quickly back across the sublimation line and then get recondensed back to the large pebbles. Then they can basically pile up at the sublimation line and can never be really released. But I think this is a more extreme case where in the more physical case, you would assume that the large pebbles are carrying the dominant mass of the volatiles, and the volatiles get released in the convective envelope. And then when they recondense, they prefer to recondense on the smaller pebbles because there are more smaller pebbles, and also because the total surface densities are higher. So that's why I think in reality it's closer to the left-hand side, where even considering recondensation, then because the volatiles are now carried by the small pebbles, and those pebbles can just be diffused out very fast. And hopefully that's a realistic enough approximation.
Sure, thanks. Yeah.
Okay, we're at the top of the hour. Let's thank our speaker again. And also, I would like to remind people that Ziyan will be staying here for this week, and they are pretty empty on the schedule to sign for meeting with her. And also, we will have another special orange seminar tomorrow, also at noon, but at Kuiper 09 across the street. And see you tomorrow.